And yeah, thanks for coming to my talk. It's the last session, but I hope I can tell you something interesting about our work on decoding these LDPC codes. And this is joint work with Chris Pattison and Eugene Tang. So to start off, we all know that quantum information is very fragile. So if we want to build a quantum computer, there's going to be a lot of noise from the environment that could mess up our qubits. And so we would typically want to use some kind of error-correcting code to encode the logical information into a bigger Hilbert space so that we can mitigate some of this effects of noise. And so there are many different error-correcting codes that are possible, and we can describe them with some parameters, including its rate and the distance. So the rate tells you how many logical qubits are encoded per physical qubit, and the distance tells you what's the minimum weight error that would cause a logical failure of the code. And recently, there has been a lot of interest in quantum LDPC codes where the check weights have constant size. And so recently there has been a lot of really good progress in creating codes with better and better parameters. So I just listed some references over there. But notably, it has eventually led to the construction of asymptotically good quantum LDPC codes, which are basically the best possible parameters where the rate is a non-zero constant and the distance is scaling linearly with the block length. But now that we have these codes, which have really good parameters, an important question is whether or not we can decode them, because when we actually want to use the code in practice, there's going to be some certain errors that occur, and then we will want to know what to do when the error actually occurs, how to correct for these errors. So that's the main question that I'm going to be talking about in this presentation. And I'd like to point out also that at the same time as our work, a similar result was found independently by two other groups, Laveri and Zamor, and also Denier, Shea, Lin, and Vidic, which actually you'll hear about in the next talk. So here's the outline for my talk. So first, I'm going to give a brief description of quantum Tanner codes, which is the asymptotically good family of codes that we're going to be decoding. And then I will give a description of the decoder, so what exactly is the algorithm we use to decode these things. And then finally, I will also give some corollaries of the fact that we have this decoder. And then I'll give some concluding remarks. Okay, so here are some basics of error correction that I'm sure a lot of you guys already know. But just to fix some notation, we're talking about stabilizer codes, which is going to be a subspace of the n-qubit Hilbert space, which is also the +1 eigenspace of some abelian subgroup of the Pauli group. And the codes that we're dealing with are going to be CSS codes, which means that the stabilizer group can be generated by two sets. So one of them is going to be purely a product of X-type polys, and another is going to be purely a product of Z-type polys. So that's the structure that we're working with. And associated with these types of codes, we can write down parity check matrices, which basically captures all of the essential information of the CSS codes. So just as an example, if our stabilizer group was X1, X2, and X2, X3, then we would have this HX matrix where the first row corresponds to the first stabilizer and the second row corresponds to the second stabilizer. These parity check matrices also define classical codes, which are the kernels of the matrices. And just to illustrate the fact that these matrices actually contain all the information we need. For example, if we want to see what the syndrome is for a given error, we can do this matrix vector multiplication, where so EZ is the locations where the Z errors have occurred, and then we multiply by the HX matrix to get the syndrome telling you which stabilizers have been violated. Okay, so to describe the quantum Tanner codes, we need to first talk about the underlying geometric complex of the code. And that is the left-right Cayley complex. So this is a two-dimensional generalization of the Cayley graph. And so to start off, we have a finite group G and two symmetric generating sets A and B. So the vertices of this complex are going to be group elements G. Then we're going to have two types of edges in this complex. So the first is going to be connecting elements G to AG, and where A is in the generating set A. And then the second type of edges, the B-type edges, are going to be connecting G to GB. So this time the multiplication is on the right. And also here we assume that the vertices can be split into two sets, so this is a bipartite graph, but this is not really that much of an assumption, because if it's not the case, we can always take the double cover of this complex, and then it will be bipartite. Okay, but because the left multiplication and right multiplication commute with each other, we can also write down a fourth vertex, which is given by AGB, and this will complete basically a square. And then we can define the squares of this complex, which is the two-dimensional structure, as the quadruples of G, AG, GB, and AGB. So there's going to be many such squares in the complex. Now, let us take a closer look at the incident structure. So what are the incident faces and edges to a given vertex G? So we're going to see that there's many A-type edges given by the different elements of the generating set A. And there's going to be many B-type edges as well. And for every single A-type edge and B-type edge, we can complete it into a square. So we'll get a figure that's kind of like this, where you have all of these squares completing for all of these edges. And in particular, then we can immediately see that the faces incident to a given vertex G is in bijection with the set A cross B. And in particular, then we can associate with this a matrix where the different entries of this matrix correspond to the different squares that are incident to G. So for example, this red square here is going to be corresponding to this top left entry, and similarly we can have this blue square and this entry in here in the matrix. So I hope that's clear how we have this correspondence. Basically, yeah. Okay, so that's basically one ingredient of creating these quantum Tanner codes. And the second ingredient is that we need some small classical codes. Okay, so basically we need a classical code, CA, of length the size of A, and CB, which is length the size of B. And then, given these two ingredients, the recipe for creating the quantum Tanner code is going to be, first we place the qubits on the faces of the left-right Cayley complex, and then we're going to be placing the checks on the vertices of the complex. Okay, so remember there are two types of vertices, like V0 and V1 vertices. So we place the Z checks on the V0 vertices and the X checks on the V1 vertices. And the Z checks are going to be coming from this tensor product code, CA tensor CB, and the X checks are from this tensor code CA perf tensor CB perf. So this might be a bit vague, but let me just do an example, and I think it will be a bit more clear. So for example, if we have the very simple case where CA is the 3-bit repetition code, and CB is the dual of this, so basically spanned by 110 and 011, then we can take the tensor product of, let's say, the 111 and 110, so we take the tensor product of these two code words, then we will get a code word on this matrix. Okay, so then basically every column is a code word of the first code, and every row is a code word of the second code. Okay, so that's kind of the defining characteristic of the tensor product code. And when we have this code word on this matrix, then we remember, like, it's in one-to-one correspondence with the faces incident to a given vertex G. So then by this association, we have a stabilizer generator on this on these particular faces. Okay, so we can do that for every single tensor product code word, and we do that for every single vertex as well. So that's basically giving you all of the checks of this code. Okay, now depending on like the quality of the ingredients that you use, you can get like different types of codes. And what was considered in Leverrier and Seymour's original construction of this code was that first we take the left-right Cayley complex to be highly expanding, and that can be done, for example, by choosing the group to be PSL2 Q to the I. And we also take some constant size generating sets, A and B. So this can all be done, but it's pretty technical. And then in addition, we fix these classical codes to satisfy a certain robustness condition, which I don't have time to get into the technical details of that, but it's just some condition that we need on the classical codes. And if this is satisfied, Leverrier and Seymour showed that this resulting code will have non-zero rate and linear distance. Okay, so one comment on this robustness thing. In their work, they proved that if you take random classical codes, you will get the parameter like delta to the 3/2 minus epsilon. So the higher the parameter, the better. And when you have delta 3/2 minus epsilon, then that's sufficient to show the distance of the code. But for our decoder to work, we needed like a slightly higher robustness condition. So then we also proved that for random classical codes using a slightly like stronger technique, then we show that you actually get delta to 3/2 plus epsilon, and that's enough to show the decoding. But since our work, there have been two other works which have basically improved this parameter to the best possible, which is theta of delta squared. Okay, so that's basically the code itself. And now I want to talk about actually decoding these things. So for decoding stabilizer codes, the general setup is that some unknown error has been applied to our code state. So we don't know what the error is, but we can gain information about the error by measuring the stabilizers. And that will basically give us a syndrome, which tells us which stabilizers have been violated. Based on this syndrome, then we can run some algorithm that will tell us some correction to apply, E tilde. And we basically succeed in decoding if E tilde is equal to E, but up to a stabilizer, because we know that stabilizers don't have any logical effect on the state. Okay, so we're talking about CSS codes, and for these kinds of codes, it suffices to decode the X and Z errors separately. So we can assume that like just an X error has occurred or just a Z error has occurred. And it's even better for quantum Tanner codes because the construction is symmetric between X and Z. So basically, we only have to decode one type of error. Okay, so this is just a more formal statement of everything that I just said. So we're given some error, which we take as an element in F2 to the Q. So basically, this is just telling us the locations of where this Z error has occurred. But we're only given the syndrome of this error. And remember, that's obtained by this matrix vector multiplication. So that's our input to our decoder. And we want to output a correction, F, that is basically equal to E up to stabilizer generator. Okay, so our decoder is most inspired by small step flip, which if you know, this is a decoder for hypergraph product codes. But if not, I can summarize this because the algorithm is quite simple. So it's an iterative procedure where in every step, we look for some flip set within the support of a Z generator that when we apply this flip, then it will decrease the syndrome weight. So basically at every step, we're trying to decrease the syndrome weight. And eventually we reach to zero syndrome. And when that happens, we will have decoded correctly. So what was proven in this paper was that for hypergraph product codes, if they're chosen correctly, then this decoder can correct all errors of weight up to square root n. And this is basically optimal for that code because the distance of the code is square root n. Okay, so we want to do something similar for these quantum Tanner codes, but we run into a problem because the syndrome weight for the code is not like a super well-defined concept. And the reason is that, well, when we actually measure the syndrome, like we don't measure like literally every single stabilizer. We would only measure the stabilizers from some generating set. And depending on which generating set we choose, well, that basically corresponds to like a basis of this tensor product code. And there could be many different bases of this tensor product. And depending on which one you choose, you would get a different syndrome. So then like, you know, what does it mean that like we're trying to decrease the syndrome weight when you can have different syndrome weights for a given error? So in order to do that, we define something called a potential function, which is basically a proxy for the syndrome weight, except it is a basis-independent quantity. So the definition of the local potential is that we consider a given vertex V and all the checks associated with that vertex. And it's basically the least number of flips that you need to do in order to satisfy all of those checks. So it might not satisfy the checks of some neighboring vertex, but we just care about this locally. And then the global potential is going to be the sum of all of these local potentials. Okay, so then we can see that the global potential is equal to 0 only if all of the local potentials are 0. And that would mean that actually we're in the code space, so we satisfy all the stabilizers. Okay, oh yeah, one more thing is that here I've defined the potential as a function of the error, but in fact, it can be computed just from the syndrome, so you don't need to know the entire error. Okay, so this is the decoder. We're given some syndrome and we want to output the correction. So in the first step, we calculate the global potential. And while the potential is non-zero, we would try to look for a flip set within some local view. So we would want to look for in either a V0 or V1 local view for some flip set that would decrease this global potential. And essentially, we just keep doing this until we reach zero potential or zero syndrome. And then we output the total correction that we've done. Okay, so the proof that this decoder works is basically follows two main steps. And the first step is that we have to show that we can actually find a flip set. So when the error is sufficiently small, so less than some linear weight, then there actually exists a flip set that we can do to decrease the global potential. And this is actually the most challenging part of the proof, and it takes up the bulk of our paper. But I don't have time to go into the details of this. Okay, and the second step is to show that when we reach zero potential, we actually go back to the correct code word. So we actually go back to the original code word that we started with. And basically, to do this, we prove kind of this lemma, which is saying that generalized small set flip type decoders work. So we're given some kind of potential function that satisfies some properties, which our potential function does. And it's basically saying that as long as you're able to keep finding flip sets, then the code word that you reach will be the correct one. So basically, you can correct all errors of weight less than a constant fraction of the distance. And for our code, the distance is proportional to the block length. Okay, so this is the second step. And if we combine these two steps together, then we arrive at our main theorem, which is that there's an infinite family of quantum Tanner codes with these asymptotically good parameters, such that our decoder can correct errors of weight up to a constant fraction of the block length. Okay, so one thing that I can prove is that this decoder is linear time. So essentially, the analysis is that there's two main steps in the decoder. The first is the initialization, where we compute the global potential. And that's basically done by computing a linear number of local potentials. And each local potential, it's only a constant weight. It's only a constant region, so that only takes constant time. And at the same time, we can store the best corrections for that particular local region. Then in the update step, there's going to be at most order n iterations of this algorithm, because at each step we decrease the global potential by at least one. And yeah, because the correction is applied within a local view, then only a constant number of these potentials need to be updated in every step. So basically, this whole update step takes linear time, and the whole thing is linear runtime. Okay, so let's talk about some corollaries of the fact that we have this decoder. And the first is the soundness property of the code. And this is saying that if we have a correctable error using our algorithm, so in particular if the error is sufficiently low weight, then the potential of the error is lower bounded by the distance of the code space. And the proof is that basically it takes at most u of e steps to get to the zero potential, and each step only delta squared bits are flipped, so the total number of flips is at most delta squared times u of e. Okay, so pretty simple proof. But what's significant about this is that this property here, first of all, is a weaker version of local testability. So we don't really expect this code to be locally testable. But if it was, what it would be saying is that this inequality holds for all E, not just the correctable errors. And secondly, this property was also called clustering of approximate code words, which was used in basically this NLTS theorem that we heard about earlier today. So in some sense, then, like our decoder provides an alternate path of proving NLTS. I mean, in particular, this soundness property of NLTS. Okay, and secondly, like a corollary is that our decoder will give a threshold for the code. And the reason is basically that we can correct a linear number of errors. So, we can correct errors of weight less than n times p star. So if the probability of error is less than p star, then it's exponentially unlikely for the error weight to be more than that. Okay, so in summary then, we've shown the existence of a decoder for this quantum Tanner codes, which is an asymptotically good a family of quantum LDPC codes. This decoder has a linear runtime, and it can correct errors of weight up to a constant fraction of the block length. So there's still some important open questions that remain. The first one is how to decrease the absolute runtime of the algorithm. So even though it's a linear time algorithm, there are some like very bad constants in front. For example, by like having to enumerate through all possible code words in some local region. And so, like, if there was a better way to do that, then we could decrease the absolute runtime of the algorithm. And additionally, for practical purposes, it would also be important to decrease the check weight of the code itself. And lastly, our algorithm is basically the same as small set flip, like for the algorithm itself, but the analysis is like really different. So maybe there will be some way of better understanding these types of small decoders so that we can see, like, for example, like when small set flip will work. So like a more streamlined way of proving these things. Okay, thanks for your attention.
We don't have too much time for questions, so let's take a few now. Maybe we can pause and then come back a few minutes before the next talk. Yeah.
For your decoder, and did you also consider noisy syndrome extraction and prove that you can decode within polynomial times of repetition?
Yeah, so in our work, we didn't consider like noisy syndromes, but we actually expect this to also be single-shot decoder. And the reason is that, well, I guess after our work, there was the work by Leveri and Zamora, which showed that like you can parallelize this algorithm. Yes. So essentially, that's saying that it's not just like one. It's not just one local view where you can make the corrections. There's actually multiple ones. So if you had some syndrome error, like even though you can't make you might not be able to make the correction in one region, maybe you can make it in a different region. So we expect that it's probably a single shot, but we didn't prove it.
Yeah. Thank you very much.
Hi, thank you for the talk. I'm just curious, in the part that you said took up the bulk of your paper, how you show that you have a V that satisfies that. Are you able to give a high-level intuition for how you go about looking for that, just as how you would approach that?
Yeah. So I do have some like slides. Okay, there's basically like 3 main steps of this thing, but I don't know if it's like very easy to describe how to do this. Essentially, yeah, the first case, like there's basically 3 cases. Like first is that you can make a single flip to decrease the potential, and that's the easiest case. And if that doesn't hold, then we look for like low overlap with some code word in some local view. And somehow, like if that's the case, if it has a high overlap, then we can also decrease the potential in some way. And that's also like fairly reasonable. But then the third case is quite technical, which uses like the expansion of the complex and also the robustness of the local code. And yeah, so I don't think it's very easy to describe like this third step very well. Yeah.
One more quick question. Yeah.
I'll just ask. So your
your decoder is linear in the length of the code, but is it also linear at the size of the syndrome? In other words, does it go faster when the error rate is low?
So does it go fast?
Linear p times n, or is it just linear in n? Like, do you have to spend the same amount of time, even if there's like hardly any syndrome data at all?
Well, it will go faster if there's less syndrome because I mean at each step you're decreasing the potential, which is a proxy for the syndrome, and so if you start off like very small, then you don't have to iterate many times to get to 0. Yeah.
Okay. Thanks. Thank you one more time.